So we're going to keep doing some hypothesis tests. In this case, we're going to be looking at a hypothesis test no longer for a mean, but rather for a population proportion. So this is corresponding to section 9.4 in our textbook. So again, this is the exact same idea as the other hypothesis test that we've already done. It's going to involve the same 6 steps with some minor modifications. We just need a couple of quick things of notation to keep track of, because this is going to look slightly different from what we've done before. So p, this lowercase p in the past has meant probability back when we did binomial, so when we're doing like the binomial distributions. But in this case, p is going to be the proportion that we're trying to predict. So it's the proportion of the population that is in some category of interest. So for example, if I want to know what proportion of the population plans on voting in an upcoming election, something related to that, asking some sort of question about that type of proportion, that would be this type of hypothesis test, if we ask some question related to the proportion of the population. Okay, P0 is going to be the population proportion. So this is the population proportion specified by the null hypothesis. And we'll see what this means in a minute when we do an example, but it's going to basically be the population proportion that has to do with whatever claim that we're going to test. So specified by the null hypothesis, H sub 0. It's basically the claim that we are going to try to test. So claim we're testing. We'll have x and n. X is going to be the number of individuals in the sample. That are in whatever that category of interest. And n is going to be the sample size. And p hat is going to be equal to x divided by n. This is the sample proportion. So this is our evidence. There's our evidence. Okay. So there are the symbols that we're going to be using. In just a minute, we'll go through the actual procedure. But I just want to remind you that this requires a few conditions be met. So it's the same conditions that we had back in chapter 8 when we were doing confidence intervals. We need a simple random sample. We need the population to be at least 20 times larger than the sample. And again, that was a relic of the binomial distribution, that our sample should be less than 5% of the total population, and we don't have to worry about replacement or lack thereof. We can only have 2 categories. So in this case, you're either in the category of interest or you're not. And the last one, we needed at least 10 individuals in each category back when we were doing hypothesis tests, and there was a little workaround for, in case that didn't happen, we could modify basically the expression of the x over n term if that condition wasn't met. You may have seen that on the homework. In this case, we have something similar. The hypothetical values in the claim that's being made, so the values in each category specified by, let's close that, specified by by P0 here. So this is the population proportion specified by the null hypothesis. It has to do with whatever claim that we're testing the validity of. If we translated this to the actual number of individuals in the two categories based on that being a proportion, we would get the following. So we would get that the values of n times p naught, so we take the proportion of the population, multiply it by how big the population is, and this would give us a number of individuals. So the values of n times p naught and n times 1 minus p naught, so that would be the proportion or the number of individuals that aren't in that given category. These are the numbers that both need to be at least 10. So we'll do that when we do our example in just a little bit. Our procedure, I'm going to start streamlining this because it's the same 6 steps. So I'll tweak this a little bit as we go, but otherwise it's the same 6 steps. First step is always state the null and alternate hypothesis. And they take a slightly different form because we're not dealing with mu anymore. There's no population mean. Now we're talking about a population proportion. So these are going to involve the letter p instead of the letter mu. So we'll have h sub 0 and h sub 1. And instead of asking a question about mu, we're asking a question about p. We'll have that p is either equal to p naught, that's our null hypothesis, or for the alternate hypothesis, p can be greater than p naught, p can be less than p naught, or p can be not equal to p naught. And again, here are our right, left, and two-tailed cases. Ours will take one of those forms. The second step is, as before, define what's weird. If we're doing the critical value method, this means actually finding the critical value. We just need to know, so we need to find that critical value. Is it a z or a t? Well, it turns out when we look at large samples from a binomial distribution, which is essentially the thing that's producing the numbers that we're getting here, it all follows a normal distribution. So this is going to be z, not t. So our critical value is going to be either z sub alpha, negative z sub alpha, or plus or minus z sub alpha over 2. If we're doing the p-value method, all we need is the significance level. So give the significance level, which is the value of alpha, the area. So that's how we define weird. This is the z-score I'll consider weird. This is the area or probability I'll consider weird. Step number 3, we need to compute our test statistic. So this is where we actually look at our evidence and see what its z-score is. And in this case, the z-score for the test statistic looks like the following. We take the observed proportion, so p hat, this is the proportion that we found in our sample. We subtract off the presumed proportion, and then we divide by the standard error, which should look familiar. The standard error in this case looks like this, p0 times 1 minus p0 all over n with a big square root of that thing. So this is what our test statistic looks like. Again, same 3 pieces. This bottom is the standard error. It's the standard deviation of this big binomial distribution of our sampling distribution. This has to do with our number from our null hypothesis, and this number has to do with the actual evidence that's given in the problem. So we'll see how that all winds up being put together. So there's our test statistic. After we compute the test statistic, if we're doing the critical value, we get to skip this next step because we have the two pieces of information that we can compare. We have the z-score of our actual evidence. We have the z-score we consider weird. We have everything we need to compare those two. So we can skip this step. But if we're doing the p-value method, we need to actually find what that p-value is. So, and as before, the p-value, which is the area to the extreme of the test statistic. So depending on whether this is on the left tail, right tail, you look to the area to the extreme of that test statistic. And we'll do, again, more examples of these down the line. But keep in mind that because we're dealing with a normal distribution again, for this one, we can use table A2. Table A3 is all we could use in the last one when we were dealing with a t distribution. But whenever we're dealing with a normal distribution, when we're dealing with z's instead of t's, we're allowed to use table A2. A2 is off limit if we're using a t distribution. That's why in the last video, our example, we can only ballpark the p-value. Here we'll be able to actually come up with a pretty good approximation of what it is. The fifth step is basically where we decide if our results are weird. So determine if our results are weird. We do that by comparing our result to the result that we were going to consider weird. So in the case of the critical value method, that just means we compare our test statistic. So our result is weird if the test statistic, which is z, is more extreme than the critical value, which takes the form of either the z sub alpha, the negative z sub alpha, or the plus or minus z sub alpha over 2, depending on, again, whether we're dealing with a left-tailed, right-tailed, or two-tailed case. So we just compare those results in the critical value method case. In the p-value method, the things that we compare are the p-value. So our results are weird, or our result is weird, if the p-value, which I'm just going to write the word p-value. This is extra confusing because for these problems, in previous sections, they use the letter p to indicate the p-value. You will have seen that on the homework if you've done these. But in these cases, p represents the population proportion, the thing we're trying to predict. So I'm not going to ever use the letter p when I talk about the p-value. I'm just going to write out the full word p-value like this. So our result is weird if the p-value is less than the significance level come on. Right, so alpha was the probability that we said we would consider weird. The p-value is the probability of getting the result that we actually got. So it's the probability of getting a result as or more extreme than the one that we found. So this is the probability of getting our evidence by chance, and this is the probability we'll consider weird. If this is smaller than this, then this is a weird result. So if this is 5% and this is 2%, 2% is considered a weird, unlikely probability. And so we will reject the null hypothesis if our result is weird. Again, the whole idea is we make the assumption that the null hypothesis is true. We go through all of this work, and we see if that leads to weird results. And if making that assumption leads to weird results, then maybe it wasn't a good assumption to make. And that allows us to draw our conclusion. Once we've decided whether or not we're going to keep that null hypothesis, we state our conclusions in plain English. Again, no statistical jargon, no weird terms. Shouldn't be talking about a p-value or a null hypothesis or anything in this sentence. It should be a plain English sentence that anybody would be able to understand. So let's do an example of one of these. So let me just zoom out so you can see all of our steps at once. It's really the exact same 6 steps. There's our procedure. It is the same 6 steps with just minor tweaks. The major tweaks occur basically in the form. In this case, we're dealing with p rather than mu in the null and alternate hypothesis, but really the big change is figuring out that we're using a normal distribution, so we're going to use z's here rather than t's, and then this is the big piece, the test statistic. This is really the major change from one section to the next. So this is the formula that gets more and more complicated. Okay, so let's zoom back in and let's do an example. Okay, good enough. So here's our example. In a random survey of Toyota owners, Toyota owners, 127 out of 180 said they'd recommend their vehicle Toyota, so they'd recommend the brand Toyota to a friend. Toyota wants to use this claim, or this information rather, to make a claim. They want to claim in some sort of ad maybe that more than 65% of owners would recommend Toyota to a friend. So they want to claim, so by they I mean Toyota. Toyota wants to claim that more than 65% of their owners would recommend Toyota to a friend. Can they make this claim? So is this a valid claim, basically? At a significance level of, let's just stick with the one that we've been doing, alpha equals 0.05. We'll do one with a different number in one of these upcoming examples. So before we jump into doing this problem, we need to check those 4 conditions that I mentioned previously. So way back up here at the top, we saw, there we go. Here we go. Here's our 4 conditions. Do we have a simple random sample? In this case, yes, I said we had a simple or a random sample of Toyota owners. Is the population 20 times larger than the sample? Well, if we go back down and look, we are saying that our sample was of 180 Toyota owners. Is that less than 5% of all Toyota owners? Are there at least 20 times that many Toyota owners? Well, 20 times that number would still be like less than, I don't know, less than 4,000. And there's certainly more than 4,000 Toyota owners. There's probably, 4,000 Toyota owners that attend C&M. So certainly our sample is small compared to the population of all Toyota owners, so we're in good shape there. We've met that condition. Let's go back up. Are there only 2 categories? Yes, there are. They'd recommend to a friend or they wouldn't. That's it. And lastly, are these 2 values both at least 10? So n times p naught and n times 1 minus p naught. Well, in this case, the value of p naught is 0.65. So our P0 is 0.65, right? That's the proportion that they want to use in their claim. So if I do 0.65 times n, which is equal to 180, that was the size of our sample. So if I multiply those together, 0.65 times 180, 65% of 180, turns out to be about 117, definitely more than 10, so we're good there. And the other one we need to do 1 minus P0, so if 65% of owners claim that they'd recommend it to a friend, that leaves 35% that don't, so the other number that I need to check is that 35%, the 1 minus 0.65 times 180, and when I do that number, I get about 63 individuals, it looks like, which is also greater than, which is also greater than 10. So both of those two values, that fourth criteria, both of those two numbers are indeed bigger than 10. So we're good to go. So let's jump into our procedure. Step 1, state the null and alternate hypothesis. So H0, H1, the null hypothesis is going to be that P is equal to 0.65, and alternatively, we want to do P is, greater than 0.65. So in this case, again, this number right here, 0.65, it's on the cusp of their claim being true versus false. They want to claim that more than 65% of owners are satisfied, and 65%, right at 65%, that's the cutoff for this claim being true versus false. So if anything less than 65% of Toyota owners would recommend to a friend, then their claim is false. If anything more than 65% of owners would recommend to a friend, then their claim is true. So the number needs to be 0.65. It's the cutoff number between their claim being false and true. That means this number has to match. Here's the statement that we're going to test. Let's assume that only 65% of owners would make a claim to a friend, and we'll check to see how likely would it be to get the result that Toyota is seeing here, that more than 65% of owners would recommend Toyota to a friend. So this is the idea for this particular problem. This makes this one right-tailed again. Okay, so in just a minute we are going to find the value of p hat. We'll need it when we actually go through in step 3 and compute the test statistic. But I want to think before we jump into this, what would even make sense? So I want to just think about this problem kind of big picture wise. Toyota's trying to use the outcome of this survey to make the claim that more than 65% of owners would recommend Toyota to a friend. So this ratio, the 127 over 180, we're going to compute that in a minute. This is our value of x, the 127, and this is our value of n, the 180. And p hat, as you'll recall, I'll do it over here on the side, is x over n. So this is the number that we're going to get from that data in just a minute. We need this number to be more than 65%, because this is the evidence that they're trying to use to back up their claim. So if I did this ratio and I found that it turned out to be only 60%, if I got 0.6 when I looked at this ratio, well then it wouldn't make any sense for them to try to claim that more than 65% of owners would recommend Toyota to a friend, when the reality is their own survey showed that only 60% of owners would recommend Toyota to a friend. So they're wanting to make this claim, and they're wanting to make it with some certainty. As you can see, the alpha is small, 0.05, so they want to be pretty darn sure that they're telling the truth when they make this claim, in this case 1 minus this number. They want to be basically 95% sure. That's kind of how alpha relates to the degree of confidence that they have. And so we need this number to be something that is bigger than 65%. Even if this number was exactly 65%, it wouldn't make sense for Toyota to claim that more than 65% of Toyota owners would recommend Toyota to a friend, because really the idea is we've got this curve over here, and 0.65 is the number that we're going to have right in the middle. We want to we want to be 95% sure that the results that we're getting are true. So if they had found that their x or p hat value, so this is the list of all the possible p hat values, if they found their p hat value to be exactly 0.65, we're really right in the center, and there's sort of a 50-50 shot of whether the value of p hat that we got, whether it's going to be sort of an above average sample version or a below average sample. Really, we need the number that we get out of this to be significantly higher than the 65%, so that even if they got lucky when they took that sample and they got a better result, they had more Toyota owners claim to recommend Toyota than the actual percentage of all Toyota owners. If they got lucky in their sample, I still want it to be so far above this number that even in the case of them getting lucky, the true percentage still would be above 65%. So basically what I'm trying to say, and hopefully this kind of makes sense, this is one of the hardest concepts to get across in one of these videos, is that the p hat value that we're going to find, we want strong evidence. What does it mean for that evidence to be strong? We're trying to back up the claim that Toyota wants to claim that more than 65% of owners would recommend Toyota to a friend. If this number that we find as their evidence is like 66%, maybe they just got that 66% from dumb luck, and the true percentage is only 63%. So they wouldn't be very confident about that result. But if in their survey they found that 80% of owners recommended Toyota to a friend in their survey, then that would be really strong evidence that at least 65%, even if we got lucky and that 80% is an overestimate, hopefully the true value is still over 65. That's a lot of wiggle room there. So it all boils down to how strong is our evidence. For this to be something that we're going to be interested in, this number, the 127 over 180, this needs to be significantly more than 65 for it to be strong evidence. If it's just right at 65 or close to 65, it's probably not very strong evidence. So this is what we should expect. We should expect this number to be more than like, a percent or two above this value, above 65%. It needs to be larger than that value. Hopefully that makes sense. Okay, so let's go back to the problem at hand. That whole conversation isn't going to affect the results, but I just want you to have some intuition about why we're going to expect the p hat value to be bigger than 0.65. In our second step, we're going to define weird, same way that we've been defining weird. If we're doing the critical value method, and this may be the last one where I do both methods. In future videos, I'll probably just do one. If we're doing the critical value method, we need to figure out what that critical value is. It's z sub alpha in this case. Z sub alpha because we're using a normal distribution. The alpha, so the z because we're doing a normal distribution, the alpha because our alternate hypothesis is right-tailed. And the value that I'm going to get, again, I can get it by looking in table A3, so let me bring that up real quickly. I want table A3. Let's insert that real quickly. Okay, I'm going to look at it and then we'll just delete this table so we don't get anything weird going on. So here's the row Z that we're interested in, right? I don't need to worry about degrees of freedom because we're dealing with the normal distribution. So here's what we're looking at. And the area in the right tail is going to be this number right here, 0.05. So there's the number I want. We just need to go down to the row labeled Z, and that gives us the number right there, 1.645. That is going to be our critical value. So that's what I need to find, 1.645. So let me undo circling those. Let's undo, let's see if this will undo adding that whole thing in. Good. Here's where we got that 1.645. So again, this is from table A3. If we're doing the p-value method, then all I need here is the significance level. So if we're doing the p-value method, I just need alpha, which is given in the problem. It was 0.05. So that's how we're going to define weird. This is going to be the z-score I consider weird. This is going to be the area I consider weird. And my picture is going to look like this. Here's the distribution of all the possible values of p hat. We're assuming the value of p hat right here is right at 0.65. So, sorry, the value of p is 0.65. That's the number we're assuming. And this is the region that we're going to consider weird over here, this top 5% of the area, so that is how big the area is. And we just found that this z-score right here is z sub alpha. Undo that, give myself a little more room. Z sub alpha equals 1.645. So this is where our cutoff is occurring. This is the weird region. This is the not weird region. If our result falls anywhere over here to the right, it'll be considered a weird result. If our result falls somewhere over here, it won't be considered weird. And that'll tell us whether or not we're going to reject the null hypothesis down the line. Okay, so let's figure out where our result falls. To do that, we need to compute the test statistic. And the formula for the test statistic we wrote down earlier. It's p hat minus p0, that's p0, over the square root of p0 times 1 minus p0 over n. That whole thing needs to be in a big square root. So the p hat, that's the 127 over 180. And I'm going to subtract 0.65 from that. So I'm going to do this as our numerator, and then I want to divide by this number down here. So 0.65, that was the p0, 1 minus 0.65, that's going to be 0.35, and then I divide by n, the sample size, which for us was 180. Let's just check this number real quickly. If I were to convert that to a decimal, 127 out of 800, or sorry, out of 180, 127 divided by 180 is about, so this number is about 0.706, 705 repeating. So this is what I mean. This number needed to be significantly above this number for us to have even a chance at having a strong claim. So in their actual survey, almost 71% of Toyota owners said that they would recommend to a friend. That's pretty strong evidence to be able to claim that at least 65% of owners are very satisfied. So even if this was sort of, again, the result of just dumb luck when they took their survey, they got a better result than the true population. Our question is going to be, is this strong enough evidence? And we'll see what the answer to that is in just a minute. This number is going to let us figure that out. So plug that number in. You can just do the 0.706 if you want, or you can actually do this fraction. Plug it into this formula on the calculator. Get your parentheses in the right place. It's a big, ugly thing. I got about 1.563-ish when I computed this test statistic. And again, later when we do this problem on the calculator, this number will just get spit out by the calculator. So I'd honestly recommend doing these problems on the calculator. It spits out the test statistic for you, and you don't have to worry about getting, parentheses in the right place and plugging into this formula correctly. So we'll do it on the calculator in just a minute, and we'll see that same 1.563 show up. Okay, so step number 4, if we're doing the critical value method, we've got everything that we need. So we get to skip this step. I've got my two z-scores. Here's the actual result of our evidence. Here's its z-score. Here's the z-score I'm going to consider weird. Is this going to be weird? The answer is going to be no, because it turns out it's to the left of this particular value. So we'll see that in just a minute. So we'll see that in step 5. If we're doing the p-value method, I need to now find the area. So we want to find the p-value, which is equal to, again, the area, in this case to the right, because it's right-tailed. Put it either way, area to the extreme. Area to the right of z equals 1.563. I just want to find, so here's where our z-score fell. Should have left more room up here in the picture. Let's go back to the picture a little bit. I'm going to rearrange this a little bit to clean this up. Okay, so there is where our z sub alpha fell. This was our definition of weird. That was the 1.645. Here's where our actual result fell. Our test statistic z equals 1.563. The p-value is now going to be this area. I need to find that area. So I want to figure out this large area here. The area to the right of z equals 1.563. So if I just round that to 2 decimals so I can use table A2, that's what we're going to do to find this. So let's look this up in table A2. So let me bring up that table. Let's open it up. We can do this a couple of ways. Let me get both of the pages that I need. Okay, here's the 2 pages that we're going to look at. Let me get them both on the screen here. I want the area to the right of z equals 1.56. Here's 1.56. So there's my number, 1.56 gives me 0.9406, and I can do 1 minus that. So do 1 minus this. Or instead of finding the area to the right of z equals positive 1.56, I can instead find the area to the left of z equals negative 1.56. So here's negative 1.5 over on this side. There's negative 1.56. And there's the number that I'm looking at. So either way, whichever one you want to do, this is our p-value right here, 0.0594. 0.0594. So let me delete all of this. All of this. 0.0594. Can remember that. So the p-value is that area. It's equal to 0.0594. Okay. So step number 5. We decide if our result is weird. Our result is not weird. It doesn't meet the criteria for being considered weird. And so if we're doing the critical value method, it's because z equals 1.563 isn't more extreme than the critical value. It's less extreme. It's less extreme than the z sub alpha value of 1.645 that was our cutoff for weird. And if we're doing the p-value method, the probability of getting the result that we just got turns out to be our p-value is 0.0594. So almost 6%, which is greater than 0.05, which is the significance level. This was our definition of weird. For it to be weird, 5% was our cutoff. Something had to happen less than 5% of the time. In this case, this happens about 5.9% of the time. So it's just big enough that it's not quite considered weird. It's really close, but it doesn't meet our definition of weird in advance. So, with that in mind, let me just say we are going to not So don't, that's what I need to write, not the word not. Don't reject the null hypothesis. We don't reject H naught because our result isn't quite weird. So in plain English, what does this mean? Let's go back up and look at the original statement of the problem. Here's the thing that we just said we're not going to reject. The null hypothesis was that the proportion of the population that would recommend Toyota to a friend is 0.65. The alternate hypothesis is that more than 65% of owners would recommend to a friend. So the alternate hypothesis is the one that supports their claim, but it turns out the evidence just wasn't quite strong enough to make the claim that they wanted to make. And so according to this, there's insufficient evidence. We're not saying that they're wrong, we're just saying the evidence isn't strong enough to support their claim. So their claim isn't necessarily false, it's just our evidence isn't strong enough to support that claim. So there's not enough evidence. There is insufficient evidence to support the claim that more than 65% of Toyota owners would recommend it to a friend. There we go. This is our plain English conclusion. Again, notice I don't mention anything about a null hypothesis here. I don't mention anything about a p-value or a significance level or anything like that. It's just a plain English sentence. There's not enough evidence, there's insufficient evidence to support the claim that more than 65% of Toyota owners would recommend Toyota to a friend. So that's our conclusion. It's really close, it's almost strong enough, just not quite there. So how do we do this on the calculator? So on the calculator, we're going to do the same thing we've been doing. Go to stat, go over to the list of tests, and we're dealing with population proportions now. So we can guess, hopefully, the correct thing to use here just by the fact that we're dealing with proportions and we're doing a hypothesis test. So, and we're using z-scores in this case, a normal distribution. So this one is going to be a 1 prop z test. On mine it's option 5. So 1 prop z test. So if I select that, a 1 prop z test, it'll ask me for the p0 that I want to use. So it'll ask for p0, it'll ask for x, it'll ask for n, and it'll ask for the form of the alternate hypothesis, which says prop not equal to p0, less than p0, greater than p0. So let's go through and fill all of these out. The p0 that we want to use is 0.65. X was 127 out of n, which was 180. And we want our proportion to be greater than this 0.65, so greater than the p0. So that is the form that we take. Hit calculate. So let me type all these in. 127, 180, and hit calculate, and we get the following things out of this. It gives us our test statistic, and for the test statistic I get 1.562690077. This was, again, our step 3. We no longer have to go try to use this crazy, increasingly crazy formula, and the formula is only going to get worse in chapter 11, so do it on the calculator. But it gives us that value. So it gives us the result from step 3, and then it also gives us the p-value. In this case, the p-value, the calculator just uses the letter p for it, is 0.059, let's delete that, 0.5906 ... Good enough. Step 4. And it also actually gives us p, what we're calling p hat. There we go. It gives us p hat of 0.705 repeating. So it gives us the numbers that we had to compute by hand up here. It gave us that number as well. So do it on the calculator. It'll give you, again, step 3 and 4, which tend to be the two kind of most time-consuming and difficult steps of the entire procedure. We still need to interpret these results using steps 5 and 6 to see what that actually means. So keep all of that in mind, and good luck on these things.